Good morning, students. So, the last class we started our Newton's laws of motion, and in this we discussed that first law and the second law, right? So, first law introduced the concept of force and inertia, and second law defines that force. That means first law gives the qualitative analysis of the force, and the second law gives the quantitative analysis of the force, right? And so then actually the effect of force, that means that effect of force also depends on that magnitude and direction and a point of application of the force. That means where that force is acting there, right? That also depends on that. So actually the force may produce the different effects. It may not only changes the direction and a magnet, that means the direction of the motion or the state of an object. The other effects also may produce. In later in the coming topics we will discuss about that. That means it may change the shape and size of the object, or it may produce the turning effects of this turning effects. So we will discuss all those effects later. Here we are going to discuss in Newton's laws in translatory motion. Only we are going to discuss about the effects produced by the force in translatory motion, right? We are confined to that only. So it may you may don't think that it only produces the translational effects. It may produce some rotational effects. That means it may set the body into rotatory motion, and then it may produce some changes in the shape and size of these objects also, right? So that we discuss in later. So then here we are confining to that concept. It should be clear. That means we are confining to the effect produced by the force in translatory motion, right? And so then that means that also depends on the point of application of the force, and then the direction and the magnitude of this force here, right? And so then that is Newton's second law and first law there. And now let us see this third law, Newton's third law. So Newton's third law. So I think all of you know this Newton's third law statement, right? So Newton's third law is, I hope it is very easy to you and it will remember for a long time throughout your life. So, but it is not that much easy to understand. So the statement is nothing but for every action there is equal and opposite reaction will be there, right? That means if a body is exerting a force on any surface, that surface also exerts the force on this agent. That means which is applying that initial force. So that means that is a simple statement there. So first write the statement. Newton's third law states that for every action there is equal and opposite reaction. There is equal and opposite reaction. So that means if you are applying a force on any object, if you are applying some force on this wall for example, the wall exerts the same amount of force on us in opposite direction, right? So that we can write this as action is equal to minus reaction, we can write. Simply we express like this. That means two forces are acting in opposite direction. They are equal in magnitude but opposite in direction. That is the significance of that negative sign there, right? So or you may write this as F action is equal to F reaction, we can write. That means force and F action is equal to F minus of F reaction, you may consider there. So that action is equal to minus reaction that is the meaning there. One is action, and here any force you may consider it as action, and the other force will automatically becomes a reaction there. So mention some points regarding this Newton's third law here. The first point, any force can be considered as action. Any force can be considered as action. Then the other force will become reaction. Then the other force will become reaction. Next. So next point, the action and reaction always acts on two different bodies. Always acts on two different bodies. So this is the most important point you need to remember. Action and reaction never acts on the same bodies. They always acts on two different objects. If you are pressing an object or if you are pushing an object, the force applied by us on the object is action. Then according to this Newton's law, we are saying that block also will exert some force on us. If you are pushing a block, for example, then force applied by the block is acting on us. So one force, say action, is acting on the block, then reaction force is acting on us. So that means one force is acting on us, other force is acting on the block. So action is, suppose, say acting on the block, then reaction is acting on us. So action and reaction never be on the same object. So if they are on the same object, then nothing is possible. That means the motion of, if an object is at rest, for example, then it will remain at rest only, because always net force should be equal to 0. Action and reaction, if they are acting on the same object, because they are always equal and opposite there. So that is the important point you need to remember. Action and reaction always acts on two different objects. That means next point here. Isolated force, that means say a single force does not exist in the universe. Does not exist in the universe. That is, force always occurs in pair. That means in the universe you never say that single force is there. So in any, you may consider from microscopic objects to the macroscopic objects, from between the force between electrons or protons level to force between planetary or stars, you may consider. So for everywhere, for every action, there is equal and opposite reaction will be there. So that means it is a single force does not exist in the universe, right? So force always occurs in this pairs only. So those are some important points regarding this Newton's law here. So their action and reaction will be there, equal and opposite forces will act, but they never act on the same object, and then they always appears to be in opposite directions. That means in opposite other objects, two objects it will act, and other one is the single force is not possible, and any force you may call them as action, then automatically the other force will become reaction. And you know the many examples for this action and reaction. As I said, if you are pushing a wall or pushing a block, then a block also will exert some force, or wall also will exert some force. And similarly, suppose say when you are walking on the ground. So when you are walking on the ground, if you observe carefully, we press the ground in backward direction, right? So that, suppose if you are taking that as an action, then ground will apply the force on us in forward direction. Like similarly, if you are swimming, during the swimming, we push the water in backward direction here with our hands, then automatically the water will apply the reaction on us in forward direction, so that we can move in forward direction. And next, similarly, in many examples you can say like this. In tug of war, if you are considering, if you are playing a tug of war game, the two teams are pulling the string. The team who will wins the game is nothing but the team who will apply more force on the ground. So if you are pushing this string here, then we should apply a more force on this ground in forward direction, because we should not move in forward direction in that game. So we should apply the force on the ground in forward direction. So we should press the ground in forward direction. Then ground will apply some force on this another in backward direction, so that we can push it in backward direction there. We have to we have to pull the string in backward direction here, right? And so that if you are applying more force on the ground, then automatically ground will supply the more reaction on us, and so that we can pull the string with the more force, and so that other team will move in our direction there, so that we can win. So that means the winning team will apply the more force on the ground in the tug of war. So sometimes they will ask about this in theoretically. So theoretical question, you may remember that the winning team will apply the more force on this string or more force on the ground. And next you may simply consider that I said this Newton's law is not that much easy as you are thinking. Suppose I am taking a simple example here. A block of mass m is placed on a horizontal surface. The block is at rest. Now can you identify the action and reaction forces here? What are the action and reaction forces acting on the block? Can you say what are the forces acting on the block? For example, If I ask what are the forces acting on the block, so you can say one force is this gravitational force, which we can represent this as mg, and other force we can say that normal reaction applied by the surface here, right? So those are the two forces acting on this block, and we know when the block is at rest means the net force acting on the block should be 0, so that you can write that as N is equal to mg. That you know already, right? Now, what are action and reaction pairs here? So if you are able to identify the action and reaction pairs in this, you can understand that Newton's law easily. That means you have some clarity. We can conclude that you have some clarity regarding that Newton's law. If you are identifying the action and reaction pairs in this example, in a simple example, a block is placed on the horizontal surface. What are action and what are reactions here? Suppose I am taking that mg as action, for example. I am taking as action as, for example, mg I am taking as some action force here. Then can you say what is reaction? So I hope most of the students will think that normal reaction is a reaction force. I hope you are also thinking the same. Normal reaction is a reaction for this mg. Is it clear? Wrong. Simply here we mentioned some points here in Newton's law. Action and reaction never acts on the same object. If normal reaction and mg or action and reaction, they are acting on the same object, so which is against the statement of this Newton's law. They never acts on the same object. They always acts on the two different objects there. That means normal reaction you can't consider it as a reaction force for this gravitational force. Got it? So those two are not action and reaction. Those are the just two forces which are acting on the object. And here in this case, those two forces are equal and opposite, so that net force acting on that object is 0. So to identify the action and reaction pairs here, you need to identify the source which is applying that force on that object there. That means, for example, if you are taking mg we know that is a gravitational force. So gravitational force means who is exerting that force? Suppose say if I am pushing this force on this wall here. So if I am pushing this wall, and suppose say if any other object is applying force on me directly, contact force. So no force will be there, because if I am pushing this wall, then wall will exert force on us, and automatically there will be force from the floor, because we are standing on that floor, right? So similarly here, this mg is gravitational force. Gravitational force means it is exerted by the earth. It is exerted by the earth. So the reaction should also be from the earth only. So the agent there who is exerting this mg is earth. So the reaction should also be on the earth only. So that is nothing. Again attracts the earth with the same force mg. That is the reaction force, not n. So clear this again. That means remember, listen this point again. mg is the gravitational force exerted by the earth on the block, or that means earth is attracting this block with a force mg. Then this block also attracts the earth with the same force mg, right? I think all of you know this Newton's law of gravitation. In Newton's law of gravitation, you know, when apple is falling towards the earth, then we say that earth is attracting that apple, so that apple is falling in the direction, in downward direction. And actually there, according to Newton's law, apple is also attracting the earth with the same force, right? That is nothing but action and reaction. If on the apple, if say 10 Newton's force is acting on the apple by the earth, then the apple also exerts the same amount of force on this earth. So that is action and reaction, means that is the action and reaction there. But there the question is simple, why the earth is not moving in upward direction is because of its heavier mass. The 10 Newton's force is negligible for that earth, so that it doesn't move. Only apple will move in forward, that means it will fall in downward direction there. So that means now similarly here, for this mg, the reaction force is nothing but the block will exert an equal amount of force on the earth, or block will attracts the earth with the same amount of force there. So that is the reaction there. For mg, again mg will be the reaction force. So mention that clearly there in that example. mg is a gravitational force exerted by the earth on the block. So its reaction is block also attracts the earth with the same force mg. Block also attracts the earth with the same force mg. Next, now for this normal reaction. So that is the action and reaction pair here, right? So that means now this earth is also attracted by the block in the same force in upward direction. So that will be the action and reaction pair there. And next is for this normal reaction. For normal reaction, which is the reaction force. So now you need to observe this. This normal reaction is the force exerted by the surface here, right? The surface will exert some force on this in upward direction. This is nothing but this force here. Surface will exert some force. Now the reaction is this block also will exert some force on this surface here, the same amount of force. Now these two are action and reaction here. So then you can't say these two are action and reaction, right? Got the clarity? So always remember that for mg, the gravitation mg is nothing but the force attracted, that means force with which the earth attracts the given object. Then its reaction is nothing but the object will attract the earth with the same force. And so this normal reaction is the force exerted by the surface, and so then the block also presses the surface in downward direction with the same amount of force here. So that is nothing but the reaction. So for this normal reaction, again the normal reaction from the block or normal reaction applied by the block on the surface will be the reaction force there. And similarly, you may consider the other examples like when the block is, instead of placing on the surface here, I am suspending from a string by using this string like this from the ceiling. See, if the block is suspended like this, then what are the action and reaction pairs here? So then again here we can mention this one force here is, I can mention this one force as mg here, mg will be there here, and you know some tension will be there here, right? And about the tension we will discuss now when we are discussing about the types of the forces. So the tension will be there. So here again the action and reaction pairs are, so for this mg, again the reaction force is nothing but what I said. So whenever you are getting the mg as one force and its reaction is nothing but same as what I said now. The force with which this object attracts the earth is nothing but reaction force, which is nothing but whose magnitude is nothing but mg only in upward direction. This mg is in downward direction. On the block it will be in downward direction. On the earth it will be in upward direction, right? So that is the reaction force there. And actually this block is pulling this ceiling here in downward direction with some tension, that we call it as a tension, the force developed inside the string, that we call that as a tension, right? And so that force is nothing but, that means it is pulling this ceiling in downward direction with some tension T. Now this ceiling also pulls the block in upward direction with the same amount of force T here. So those are action and reaction here. This block is pulling the ceiling in downward direction. Suppose if you are hanging from some ceiling with some help of either string or with the help of some rod suspended from the ceiling, then we will pull the string or we will pull the ceiling in downward direction. That is action. Then ceiling also pulls us in upward direction with the same amount of force. So that will be the reaction. So similarly now this is action and this is reaction we can consider here. The force exerted by the block on the ceiling, which is in downward direction, the force exerted by the ceiling on the block, which is in upward direction. So that we can consider as action and reaction pairs there. So like that, as I said, when you are walking on a road, then on the ground will, that means we press the ground in backward direction. So that we may consider it as an action. Then ground will apply the force in forward direction. That you may consider it as a reaction, right? So those are some examples for that. Action and reaction examples. And next, here actually we define this conservation of momentum. Just we define here, and in detail we will discuss later here. Just I will define this conservation of linear momentum. Conservation of linear momentum. So this conservation of linear momentum means just I will define here because it is related to that Newton's laws only. And then actually we will discuss more about the conservation of linear momentum later. Separate topic is there for us, collisions and conservation of linear momentum. There we will discuss in detail. Just I will introduce the conservation of linear momentum principle here. So there, suppose if I am taking this Newton's second law. So our Newton's second law is nothing but F external is equal to dP by dt we can write, right? That means the external force acting on an object or a system is equal to rate of change of momentum of the system. So right, now here what I am taking is if F external is equal to 0, that means there is no any external force acting on the system. If no external force acts on the system, then from this Newton's second law what we can write is dP bar by dt is equal to 0. That means rate of change of momentum should be equal to 0. And therefore from this we know that differentiation of a function is 0 means then we can say that this function will be a constant value. So that is nothing but we call conservation of linear momentum here. So P initial is equal to P final we can write. That is a conservation of linear momentum we can write. So first note down this, then I will say the statement here, conservation of linear momentum statement. First note down this and after that write, the conservation of linear momentum principle states that, the conservation of linear momentum principle states that if no external force acts on the system, if no external force acts on the system, the linear momentum of the system, remains same. So that means this is actually a very important and basic principle in physics, conservation of linear momentum. Like we discussed conservation of angular momentum later and conservation of energy. So all these are the basic principles here. So like that, this is also one of the basic principles here. So we can simply say by using this Newton's law like this. So when external force is 0, then dP by dt is equal to 0, and so that this momentum of the system is constant here, right? And so more about this conservation of momentum we can discuss it later. And here simple problems will be there, like suppose if you are firing a gun, then the bullet will travels in forward direction and the gun will travels in backward direction here, right? That is because of conservation of linear momentum we can say. Because initially the gun is at rest. The gun is at rest means initial momentum is 0. Then final momentum should also be 0. So that means now here if I am applying this conservation of momentum for this, so initial for this gun here, the initial momentum is 0. Then if bullet is traveling in forward direction here, then its momentum is mv. Then gun should travel in backward direction to conserve the momentum. So then suppose I am taking this mass of this bullet is small m and velocity of the bullet is this v, and mass of this gun as capital M and velocity of this gun as v, recoil velocity that we called, and therefore this mass into velocity is equal to m into v you can write. Therefore this is the velocity of the gun here. Velocity of the gun is equal to mv by mass of the gun we can write. So like that we can calculate this velocity of the gun here. So that means that is why the recoiling of the gun will take place. So if you are firing a bullet from the gun won't be at rest, it will recoil. So generally in the when you are firing the gun, that is why some training is required to fire a gun. You can't fire it easily. as we are thinking. So some training is required to hold the gun in a particular position. So right, because to avoid the recoiling of the gun, sometimes may cause the injuries to the person who is firing that gun. Right. So for that the proper position of the gun is required there. So that is a simple example for that. Or similarly, if suppose a shell is at rest, a bomb is at rest, which is exploding into two pieces, then definitely those two pieces should move in opposite directions there, right? Because initially the shell is at rest means its momentum is 0. Now final momentum should also be 0. Final momentum should also be 0 means if one piece is traveling towards left or other piece travels towards this right here, and so that their initial and final momentums will be equal, and that means 0 you will get. Final momentum also you will get 0. Like similarly, some problems will be there, like you are throwing some bag on a ice. If you are standing on a surface of the ice, for example, and if you are throwing a bag on the ice in one direction, that means the total surface is ice. You are standing such a ice surface. If you are throwing the bag in one direction, then automatically we will move in other backward direction there, because initially our system, that means ourself and the bag, that is our system now. So that momentum is 0. Now we are throwing the bag means for the system now we are giving some momentum. So then what momentum should be 0? The final momentum should be 0. So that this person who is throwing the bag will move in backward direction there. So that is some examples for the conservation of linear momentum. And simple such a problems may be there here, but actually in detail about this conservation of linear momentum we will discuss it later. In collisions we will discuss that. And from this only we can prove that action is equal to minus reaction, we can prove that. Like simply if I am considering that that Newton's second law, that means based on this Newton's third law, we can write here. If suppose I am taking this two particle system here, those two particles are moving here without any external force. So that this m1 plus m1 v1 plus m2 v2 is equal to constant, we can write. That means we are taking this, if external force is equal to 0, then momentum of system is a constant. Then we are taking such a two particle system, for example, then two particles are moving such that m1 their momentum is constant. m1 v1 is equal to m1 v1 plus m2 v2 is m1 v1 plus m2 v2 is equal to constant. Now here what I am saying is, suppose I am differentiating this equation here, then m1 into dv1 by dt plus m2 into dv2 by dt is equal to 0, because it is a constant, so it is 0 we can write. And so that this is m1 a1 plus m2 a2. This the rate of change of velocity is nothing but our acceleration here. So I can write this as f1, force acting on the first object, and force acting on the second object. So that is equal to 0. And so that this is equal to f1 bar is equal to minus f2 bar, we can write here. That means that forces are equal in magnitude and opposite in direction here. The force acting on first object and force acting, that means there will be some interaction force between those two objects only. Here external force is not there, only those two objects are interacting. Like for example, you know, the basic point, like unlike charges attract each other or like charges repel each other. For example, I am taking such an object here. Say one is a positive charge and other is negative charged object here. Minus q and plus q charges, let us consider. Now these two bodies will attract with each other, right? These two forces will be there on these objects here. Say f1 is like this and then f2 will be like this. So then that is the example here. Those two forces are, because of that internal force only, those two objects are moving. Now we are taking them as a system here. These two objects are considered to be system here. We are taking them together as a system. So when you are taking them together as a system, then this is V1 you may consider here, this is V1 bar and V2 bar, vectors. So these are vectors we are taking here, right? So that this M1 V1 bar plus M2 V2 bar should be equal to a constant value, because there is no any external force acting on the system. The only force we are taking them as internal force only. That means only the mutual attractive force only we are considering them. And so that then we can write like this. So that this action is equal to minus reaction, we can prove here. So that is in the absence of external force, then this is the situations there, right? And so now here let us discuss now about this forces here. These are the simple statements of this Newton's laws and this conservation of linear momentum. So about this linear momentum, this I am saying again, remember this linear momentum is a very important principle in physics. Like the basic principles will be there. Conservation of linear momentum and conservation of angular momentum and conservation of energy, like conservation of mass. Some basic principles will be there. Those are very important principles in physics. And we will discuss very interesting and important models based on the conservation of momentum later. In that separate topic is there for that. And next I am going to discuss about these types of forces here. So types of forces. And actually these forces can be classified into in a different ways. We can classify the forces in a different ways. We can classify them. So in general, we define them into 4 types, but in mechanics, we define them in another way. So right. So first I am defining them in general here. So in general, these forces are classified in 4 types. So in general, the types of forces are gravitational force, electromagnetic forces, and the next one is say nuclear force, and the third one is weak forces. Right. So this is the one type of classification or the general classification of these forces here. Gravitational force or the electromagnetic force, nuclear force, and the weak forces. And for us in mechanics, we will classify them in another way. So first let us see in detail about this. Briefly I will explain what are the different types of forces here. So that means whatever the type of force you are facing or you are getting throughout your study or throughout your life, all those forces will belong to any one of these 4 forces. So that is why we are calling them as general classification or the basic classification of the forces here. This is the basic classification of the force. All those forces are in general or the basically they are classified into these 4 types. So whatever the force you may consider here, any type of force that belongs to any one of these 4 types. Right? And so now here out of them these 3 forces are major forces, and this force will be a weak force, and its role will be there inside this nucleus or when the elementary particles are transferring from one particle to another particle. So its role will be there. That means in our that means this force will arise rarely. That means during the atomic like a elementary particle transmissions only. And whereas these forces are major forces, and mainly we will get these forces regularly. Like gravitational force, you know, the attractive force between 2 masses. If 2 masses are attracting with each other, then that we call such a type of force, we call it as a gravitational force, right? And next, this gravitational force is we can say that it is the weakest force. The gravitational force is the weakest force in the nature, but it is a long range force and it is always attractive force only. Then gravitational force, there is no question of repulsion, right? It is always attractive. Every mass attracts every other mass only. So just you may mention those points there regarding that. And we will discuss in detail about each force in those particular topics. Gravitation, one topic is there. So we will discuss about the gravitational force in detail there. And similarly, electrostatics, we discuss the electric force, and magnetism, we discuss about the magnetic force, and radioactivity, nuclear physics we need to study, and there we discuss about these weak forces and these nuclear forces there, right? So then just I am briefly I am explaining, I am giving some information about those types of forces here. So mention that gravitational force, it is always, the gravitational force means it is attractive force between 2 masses. It is always attractive in nature. It is always attractive in nature. It is the weakest force. It is the weakest force in the universe, but it is a long range force. But it is a long range force. And some other properties are there, just these are sufficient to remember you. That means remaining properties we will discuss in that particular topics. Next, electromagnetic forces. Electromagnetic forces. So electromagnetic force means, as we discussed, the attractive force between two charges or between two magnets. So that we call electromagnetic forces, either electric or magnetic forces. And those are, in olden days, they are studied as two separate branches. Electricity is separate branch and magnetism as separate branches. And nowadays we are combining them together. That means both are related only. That means because current carrying coil will produce as a magnetic field, and changing magnetic field can produce a current or electric field. And so that they are not separate branches, they are a single branch only, we are studying them. So that is nothing but we are naming it as electromagnetism or electromagnetic force. That force is called the force between two charges or two magnets. And so now it is either attractive or repulsive. The force may be, electromagnetic force may be either attractive or repulsive depending on the nature. And next, it is stronger than the gravitational force, but it is weaker than that of nuclear force here. This is electromagnetic force. And it is also a long range force. It can act over a long distance also, right? So it is very much stronger than that of gravitational force. In that particular topic, we will calculate that ratio also, how much it is. So nearly we will get 10 power 40 times that of stronger than that of this gravitational force you will get, right? And that is why whenever we calculate the force between two electrons or two protons, or the electron and proton, we don't consider the gravitational force, because the gravitational force is negligible when compared to that of this electromagnetic force. And next is nuclear force. So nuclear force means this force is responsible for the holding all the nucleons together. Inside the nucleus, what are the particles present? So protons and neutrons will be there inside this nucleus, right? So those protons are positively charged and there exists some repulsive force between them. So but we know that protons are not moving away from each other, right? That is because of this nuclear force. So nuclear force will hold all the nucleons together. Even though there is some repulsive force between the positively charged protons, this nuclear force will hold all the nucleons together. So that is nothing but we call the nuclear force here. So this nuclear force is the strongest force in the nature. So may just mention that nuclear force holds all the nucleons together in the nucleus. It is the strongest force in the universe. But it is a short range force. That means it acts within the nucleus only. If the distance between the nucleus, two nucleons is more than that, then this force doesn't appear there. That means they become weak. So there, if the size of the nucleons, that means the size of this nucleus is nothing but of order Fermi, right? 10 power minus 15 meters. That Fermi is nothing but. So when the distance between two nucleons is in that order of order Fermi, then only these nuclear forces will be considerable. So if the distance between them is more than that, if suppose 1 meter, two protons are separated by 1 meter distance, or a proton and neutron is separated by 1 meter distance, then this nuclear force are negligible. We won't consider the nuclear force between them, right? So that means that is why it is said to be a short range force. When distance between them is very small, then only this nuclear force will be there. So that we can conclude that generally this nuclear force will lies only within the nucleus there. So there outside the nucleus it doesn't exist. So that is, but it is the strongest force in the nature, this nuclear force is. And next is weak force. So this weak force generally arises during the transformation of one elementary particle into other elementary particles. Like suppose a proton will convert into a neutron inside the nucleus, and a neutron may convert into a proton. It's a continuous process, continuously that takes place inside the nucleus. So you will get in like in nuclear chemistry you will get all those details there. So inside the nucleus what we are thinking, proton and neutron, they are not confined as a proton and confined as a neutron for long time. A proton converts into neutron and a neutron converts into proton with the emission of some particles, some other particles. And so then that during that process these weak forces will arise there, and whatever the particles what we are learning, like fundamental particles means, I think you may know electrons and protons and neutrons, these are the fundamental particles, right? Elementary particles are there, that means the particles which are smaller than that of these protons, electrons and neutrons. So that means like a lot of particles are there, nearly up to now I think nearly some around 120 plus such elementary particles are there, in addition to these protons, neutrons and electrons, like mesons, pi mesons and mu mesons, borons, kryptons, and such a lot of particles are there, elementary particles are there. So then between them, when they are transforming from one form to another form, such a weak forces will arise. And so then this we won't get any information, that means full information at this level. If you are going for any higher studies related to that, then you will get the more information about this weak forces there, right? So this is the basic classification of the forces here. But in mechanics, we will classify the forces in another way. Like in mechanics, we classify them as field forces, contact forces and connecting forces. Whenever two objects are connected, then some force will arise between them. So that is said to be types of forces in this mechanics. So that means mention that. Next, in mechanics we classify the forces as the first one field forces, and the second one contact forces, and the third one connecting or attachment forces. So these are the types here, and so just think about those types and I will give the details about these forces in the next class, right? So in mechanics, these are we classify those forces into these types, and whatever the force we are discussing, that belongs to any one of these four forces here. This is the basic classification of the force. You may consider friction, you may consider the elastic force, or you may consider the spring force, or you may consider the normal reaction. Whatever the force you know, or whatever the force you are going to learn in future also, that force definitely belongs to any one of these forces here, right? So that is this is a basic classification of the force. In our mechanics, we classify the forces into like this: field forces, contact forces, and then this is connecting forces. So simply briefly you can understand that field forces means physical contact is not required, like our gravitational force, electrostatic force or magnetic force. Contact forces means physical contact is required here, and this is connecting force means when two objects are connected by either string or spring, then this connecting force will arise there, right? So we will go in detail, that means I will explain in detail about these forces in our next class, right? Thank you.